Hi, welcome to another short video for Calculus for All. Today's topic is the instantaneous rate of change. Now, so far we've been comfortable with determining the average rate of change between 2 points. That is, the first point being A, f of A, and the second point being B, f of B. And we discovered that the average rate of change is simply the slope of the line segment joining those 2 points. That is the slope of the secant. And we also discovered that there are a variety of ways which we could determine the average rate of change. And simply, if I just add let's say a little graph here, and we know that the formula for the average rate of change, that is the slope of the secant line, that is delta y over delta x, or between our 2 points, A of f of A and B of f of B. It's just f of B minus f of A over B minus A. And then we also discovered that it may have been easier, rather than writing B and f of B as a point, we'll anchor the first point A f of A, and we'll determine that the other point B is a distance h away from point A. Now, let me just graph my point over here, and there's A, and that would be its y coordinate f of A, and B is really a distance h away, so its x value is really A plus h, and its y value would be f of A plus h. So h would be our distance between the 2 points, and then we'd have, of course, f of A plus h minus f of A as the distance in terms of the y value between those 2 points. And of course, the line segment between those 2 points, we've just determined the slope of the secant. Now, my friend Newton just popped up and says, yes, that is nice, but most times I don't want to know my average rate of change or my average velocity. I want to know my velocity at a specific moment of time. That is, I want to know my instantaneous velocity or my instantaneous rate of change. Now, that is a great question. So what we want to do is, rather than determine the average velocity or the average rate of change between 2 points, A and B, we want to pick one point, let's say A, and we want to determine the velocity exactly at A. So rather than determine the slope of the secant line between 2 points, we actually want to determine the slope of the line at one point. And as you notice, Newton popped up and says, hey, I know what we call that type of slope. That line that just touches at one point on my curve is called a tangent line. And I'll put my point in there and just demonstrate. Here's my A, f of A, and of course all we want to do is find the slope of this tangent line. So this would give us the instantaneous velocity at a point A, f of A. Now, Newton is very prominent in saying, hey, you got a problem here. We know how to calculate a slope. To calculate a slope is rise over run, or delta y over delta x, but we require 2 points. And he's saying that to calculate a slope, you require 2 points, but you're trying to calculate the slope by only using 1 point. And he doesn't think it can be done. But I'm reminding him that there's a neat mathematical tool that we've already worked on that provides a beautiful way to solve this problem. So what we're going to do, we're going to build upon what we already know. We can take out our second point B, and if we calculate the slope of the line segment between this A and this B, we actually calculate the slope of the secant, the average rate of change. But if I take my point B and I start bringing it in closer, you'll notice that the slope of the secant starts to approximate the slope of the tangent. So in other words, we're going to take our point B and we're going to bring it in closer and closer to our point A. And every time we bring it in closer, we will determine the slope of the secant. And what we really want to do, we'll know we'll get the exact answer if we bring the point B so close to the point A. Now remember when we started writing h representing the x value distance between the 2 points? In other words, we want that distance h to get smaller and smaller. Ideally, we want that distance to go to 0. Now let me clear the screen, because we've done that before. We call that limit. So what we want to do is we want to take our average rate of change, our formula for the slope of the average rate of change. We want to use the one that involves h, but we want the limit as h goes to 0. So this way, we actually do use the technique using 2 points, but as we allow h to go to 0, we will determine the limit as if we only had 1 point. So the average rate of change formula, we will use the formula f of a plus h minus f of a over h. All we want to do to create the instantaneous rate of change formula is add one small piece. We're going to add the limit as h goes to 0 in front of our expression. Now, it becomes a very simple technique. Graphically, there's our point A, and like I said, we'll pick a point B, and all we want to occur is to bring this point closer and closer together. So you can imagine the line segment joining those 2 points, which is the average rate of change. But as I bring this other point closer and closer, that is, I allow the distance h between those 2 points to go to 0, what I will determine is the slope of a tangent line that basically just touches my graph at point A. Beautiful. Now, the best way to get a gut feel of this, to see how it actually works, is to do an example. So we will determine the instantaneous rate of change of our function f of x equals x squared, and we'll do it at the point x equals 2. So I'm just going to draw a nice little graph so that we can visualize what's going to occur here. Let me add the point 2, 4 on our expression. Now we know a new instantaneous rate of change technique is this limit. We know that the value that we want to substitute for our point, that is a, is actually going to equal 2. So I'm going to plug in 2 plus h into my function. Then I'll plug 2 into my function. I'll subtract that, divide by h. So let's do some algebra. We'll expand this across. We'll do some house cleaning. Now, this is a limit, and we know this actually is an indeterminate. So we have techniques, and we'll notice that our h's are going to cancel out. Now I can actually evaluate the limit. And so as h goes to 0, this limit goes to 4. So this is actually the instantaneous rate of change at x equals 2, or in other words, this is the slope of the tangent line to my function at the value x equals 2. Now I'm going to show you something really, really neat. I'll start where I started before. Let me just bring it up. But before we substituted 2 in for h, I'm going to go very abstract here. I'm actually going to say I don't know what the value of a is. In fact, I'm going to say the value of a is really x. Very abstract. Now in the previous example, of course, x was equal to 2, so I'm going to leave it as x. But I'm going to substitute x plus h into my function and evaluate this limit. So more algebra. There are no numbers, so it looks a bit scarier, but trust your algebra. I'll do some house cleaning. There's a limit, so I will cancel out my h's. I'll allow this h to go to 0, and I get an expression 2x. So this says, hey, for this function, f of x equals x squared, the formula to calculate the instantaneous rate of change, that is the slope of the tangent line, is simply the expression 2 times x, where x is the value that you're interested in. And you'll notice when we did it when x equals 2, if I substitute in 2 for x, I get 2 times 2, which is 4. So this expression has more power to it. You give me a value for x, and I can tell you the slope of the tangent line at that x value on the function f of x equals x squared. For example, if x is 10, the slope of my tangent line would be 2 times 10, or 20. This is really, really powerful. Just cool. So let me just bring this thing up. I think this is a more important expression. This formula here says, hey, I can calculate the instantaneous rate of change, that is the slope of the tangent line, to any function f at any point x by evaluating this limit. Later on, in the next couple of videos, we will be doing 2 or 3 really good examples to allow us to become more comfortable with this expression. Thank you for watching. Hopefully it was helpful.